So rates of change, which is, let's say, a practical application, I guess, of calculus. Because if you remember, the derivative is simply a rate of change, how something changes with respect to something else. Now, in extension 1, sometimes we need to use more than one rate of change to come up with an answer. Sometimes we have to combine them, like a chain rule or implicit differentiation. So, using that idea, that if I want to find dy dt, I could find dy dx, I could find dx to t, multiply those together, and we'd get dy to t. So let's look at this example. We've got a block of ice in the form of a cube. I guess you could call it an ice cube. Makes sense. One edge is 10 centimetres long, and it's melting at a rate of 1 millimetre per second. We want to know what rate the volume's decreasing once that edge gets to 5 centimetres, so it's sort of half of it's melted away. So there's my cube. Side is x. Okay, let's read through the question. The first thing, I guess, is what are we trying to find? We're trying to find the rate of change of the volume. Well, that would be dv dt. So somehow we have to link volume and time together. So what else have they told me? They've told me that dx to t, the rate of change of the edge length, is going down at 1 millimetre. Well, 1 millimetre, of course, is 1/10 of a centimetre. So, and it's decreasing, so we'll make it negative. So we know dx to t is negative 1/10. So I want to find dv to t. I've got dx to t. So if I could link volume and the side length and come up with an equation for that, we can complete our rate. Well, of course we can. Volume of a cube is just x cubed. And so I could find dv dx by differentiating. We get 3x squared. We can sub that in, and we come up with a relationship there. We can find dv to t. It's in terms of the edge length, but minus 3x squared on 10. Now they've asked us for the specific rate when it's 5 centimetres long. Well, now it's just a substitution. So when x equals 5, that dv to t would become negative 7.5. So we know, all right, at that point in time, it'll be decreasing at 7.5 centimetres cubed per second. A vessel's in the form of an inverted cone. Vertical angle 90 degrees. First thing they want us to do is come up with an expression for volume. So there's my inverted cone, and there's some water inside it. We want to find the volume of the water. So what do we know? They told us the depth of the water is x. Okay. Volume of a cone, who remembers it? Yeah. 1/3 pi r squared h. Remember, a pyramid is always 1/3 of the prism. So, I mean, you can think of a cone like a circular pyramid, and a cylinder is like a circular prism. So 1/3 pi r squared h. All right, well, if it's the blue little cone here I'm trying to find, we know the h, got to find the radius. Well, if that bottom angle there is 90 degrees, then I must have a 45-degree right-angled triangle there that I've just drawn in, which makes it isosceles, so the radius must be x as well. So we get our 1/3 pi x squared times x, so we just have a 1/3 pi x cubed. There's an expression for the volume. All right, so we now know that water is being poured in at a rate 0.2 centimetres cubed per minute. We want to find how the depth is increasing. So the depth is increasing. That's dx to t we're trying to find. They've told us dv to t is going up 0.2, which is 1/5. So I know dv to t, I want dx to t. So it looks like the link I want is between volume and x, which we just worked out in part A. If I differentiate part A, I'll get dv dx is pi x squared. Pi x squared. So sub that all in, and we now have an expression for the rate of change of the depth. We want the specific time. It's there somewhere. Where is it? There it is. 4 centimetres. So sub in 4, and we get 1/80 pi. Well, that's our exact one, I'll leave it like that. I mean, you could go to your calculator. But 1 on 80 pi centimetres per minute. A spherical bubble makes life easy because if it's a sphere, we've got a formula for that. Volume is increasing at a constant rate, but the surface area would not be going up at a constant rate. So we want to know the rate of change of surface area. So I'll call that S for surface area. ds to t is what we want to find. They've given me dv to t. dv to t is 70. So if we could link volume and surface area, well, that's not quite as easy, but what I can do is I can link surface area with radius. I can also link volume with radius. So this time if I use 3 different rates, I can come up with a formula. So let's find all those. Volume of a sphere, 4/3 pi r cubed, dv dr, 4 pi r squared, which by an amazing coincidence is surface area as well, is 4 pi r squared. ds dr is 8 pi r. Sub that all in, and we get the rate of change of the surface area is 140 on r, inversely proportional to the radius. So as the radius gets bigger, the rate of change gets smaller. We want the specific time when radius is 10 millimetres. So sub that in, we get a nice neat 14 millimetres squared per second. Okay. So that's our rate of change idea. So trying to link different derivatives together to come up with a formula for finding a rate of change.